Okay, so this is a stream along, read along, stream along, merrily, merrily we row, and it's an introduction to chapter 6. And I hope it's going to be me sort of reading the book with commentary, okay? So chapter 6 has 9 sections. It's all about starting the big project of solving first choosing a problem. And the problem that we're going to choose is writing a calculator, which eventually should be a graphing calculator. So that's pretty cool. And next term, a graphing calculator. But for now, we just want to be able to parse, that is, interpret expressions correctly and simply and efficiently, in that order, as usual. So here we go. Writing a problem starts with the problem. And so we're going to choose, I'm just going to skip over that because we know what we're going to choose. We're going to choose writing a calculator. And why? Well, you can read about that. But let's talk about the stages of development. Analysis, design, and implementation. So figure out what should be done and write a description of your current understanding of that. Understand the problem. This is sort of like Polya's method, the 4 steps of Polya, which are 1, that's my 1, understand the problem. 2, make a plan. That's my second finger. The third is carry out the plan. All right, and if that's successful, then you should look back. That's step 4. If it's not successful, you go back to step 2, which is to make a plan. So, design and implementation. Well, create an overall structure for the system, deciding which parts the implementation should have, and how those should communicate. As part of the design, consider which tools, such as libraries, can help you structure the program. Yeah. It's all about the STL library for some people, and yeah, I'm understanding that more and more. Implementation is to actually write the code, debug it, and test it, and that it actually does what it's supposed to do. But yeah, notice the design comes first, and so don't run right into implementation without thinking about what you're going to do. And then you may have to rethink what you're going to do because you tried to carry it out and it didn't work. So you went back to step 2 in Polya's scheme, make a plan, that is design. Okay, so strategy. Here are some suggestions that, when applied thoughtfully and with imagination, help with many programming projects. What is the problem to be solved? Is the problem statement clear? Does the problem seem manageable? To make it manageable, try breaking the problem into manageable parts. Do you know any tools, libraries that might help? Look for parts of the solution that can be separately described and potentially reused in several places, right? And to find such parts requires experience, so we provide many examples throughout this book. We've already used vector string and IO streams. This chapter gives us the first example of design, implementation, and use of program parts provided as user-defined types. So we're going to be defining token and token stream. That's a big part of this project. Chapters 8 and 13 through 15 present many more examples together with their design rationales. For now, consider an analogy. If we were to design a car, we would start by identifying the parts, the wheel, the engine, so the objects, the classes we're going to be defining, and then we would assemble it, the complete car. I've seen how they work together. There are tens of thousands of parts in a modern car. Real world program is no different in that respect, except of course that the parts are code. Yeah, and yeah, if you're writing code for a car, yeah, that's worrisome. There's a lot of that going on. All right, so designing and implementing such parts is a major theme of this book. Software development in general. See discussions of user-defined types in chapters 9 and 14, and generic types in chapter 20. Okay, well, that's a long ways off. Build a small, limited version of the program that solves a key part of the program. When we start, we rarely know the problem well. We often think we do, but don't we know that what a calculator program is? No, we don't. In fact, oh my goodness. Yeah, modern calculators have some pretty complicated algorithms, which we'll talk about maybe sometime. Anyway, okay, so we built a small limited version, and the idea there is, start small and find out what the problems are. So this is that sort of, it doesn't work, so go make another design feedback loop, right? See if the details of a program statement need changing, make the problem manageable, right? Which, use simplicity. It's rare to find that we have anticipated everything when we analyze the problem and made the initial design. We would like to take advantage of feedback that, does it work, it doesn't work, go back, make another plan, or revise the existing plan. If you've made your code simple enough and manageable enough, it should be easy to revive without scratching it entirely, right? Sometimes such a limited version aimed at experimentation is called a prototype. If, as is likely, our first version doesn't work or is so ugly and awkward that we don't want to work with it, we throw it away. Make another limited version based on our experience. Repeat until we find a version that we are happy with. Do not proceed with a mess. Messes just grow with time. Yeah, you want a solid foundation. So build a full-scale solution, ideally using parts of the initial version. The ideal is to grow a program from working parts rather than writing all the code at once. So the alternative is to hope that by some miracle of untested ideas, you'll strike on a working solution. Good luck. Okay, so I'm going to take a break here. I think there's a way of pausing this thing. Maybe not, huh? So I'm not sure if I'm even recording. Let's see, this is my first attempt at using OBS to record things, and